Hello, dear students, welcome to massive open online course on SWAYAM in chemistry. Myself Preeti Kiran, PGT Chemistry from Kendriya Vidyalaya No. 1, Air Force Station, Hindon. Dear students, in the previous module, you have studied about the dependence of rate of reaction on concentration. We defined rate law and rate constant and differentiate between the molecularity and the order of a reaction. Today, we will discuss and learn about how to derive integrated rate equations for the zero and first order reactions. Determine the rate constant for zero and first order reactions and will determine the half-life of a reaction and then the pseudo first order reactions. Now first of all, integrated rate equations. We have already noted in the last module that the concentration dependence of the rate is called differential rate equation. It is not always convenient to determine the instantaneous rate as it is measured by determination of slope of the tangent at point t in the concentration versus time plot. This makes it difficult to determine the rate law and hence the order of the reaction. In order to avoid this difficulty, we can integrate the differential rate equation to give a relation between directly measured experimental data and concentration at different times and rate constant. The integrated rate equation is used to determine the rate constant of the reaction. Also, it is helpful to calculate the exact time when reaction is either complete or at any intermediate position, that is 25% or 50% or 90% completion and vice versa. The integrated equations are different for the reactions of the different reaction orders. We shall determine these equations only for zero and first order chemical reactions. First of all, let's take up zero order reactions. A reaction with zero order means that the rate of the reaction is proportional to 0 power of the concentration of the reactants, that is independent of the concentration of the reactants. Let's consider the reaction. R gives P, where R is the reactant and P is the products. The rate expression will be minus d molar concentration of R upon dt. It is equals to K molar concentration of R raised to power 0, as any quantity raised to power 0 is unity. Therefore, rate is equals to minus d molar concentration of R upon dt will be equals to K into 1 and hence d with molar concentration of R is equals to minus K dot dt. Now integrating both the sides, the molar concentration of R is equals to minus Kt plus I. This is the equation number 1 and there I is the constant of integration. At t equals to 0, the concentration of the reactant R is equals to R0 or R0, where R0 is the initial concentration of the reactant. Now substituting this value in equation 1, R0 is equals to minus K into 0 plus I. Therefore, R0 is equals to I. This way we get the value for the integration constant. Now substituting this in the equation, R is equals to minus Kt plus R0. Now comparing the equation 2 with the straight line equation, y is equals to mx plus c. If we plot the graph between molar concentration of R against t, that is time, we get a straight line graph and that shows variation in the concentration versus time plot for zero order reaction, with slope is equals to minus k and intercept equals to R0. Now the graph is in front of you, which will help you to find out the value of slope and the intercept. Further simplifying the equation 2, we get the rate constant K as K is equals to R0 minus R by T. This is equation 3, where R naught is the initial concentration and R is any concentration at time t. All zero order reactions obey the equation number 3. If the values of R naught, R and T are known, then the value of the rate constant can be easily evaluated. Zero order reactions are relatively uncommon, but they occur under special conditions. The example of the zero order reactions. Some enzymes catalyze reactions, and the reactions which occur on metal surfaces are a few examples of the zero order reactions. These type of the reactions generally occur in heterogeneous systems. For example, the decomposition of the gaseous ammonia on a hot platinum surface is a zero order reaction at high pressure. The equation is in front of you. 2NH3 gives N2 plus 3H2. All are in the gaseous state. The rate of the reaction is given as rate is equals to K molar concentration of ammonia raised to power 0. That means the rate is equals to K, because anything which has 0 power becomes unity. In this reaction, platinum metal acts as a catalyst. At high pressure, the finely divided metal surface, that is, platinum surface, gets saturated with ammonia gas molecules. So, a further change in the reaction conditions is unable to alter the amount of ammonia on the surface of the catalyst, making the rate of the reaction independent of its concentration. Let me take another example of zero order reaction. The thermal decomposition of the hydrogen iodide on gold surface is another example. The first order reactions. Now, in this class of the reactions, the rate of the reaction is proportional to the first power of the concentration of the reactant R. For example, the reaction is R gives P, where R is the reactant and P is the product. Now, the rate of the reaction is given as rate is equals to minus D molar concentration of R upon dt equals to K molar concentration of R raised to power 1. Therefore, minus dr upon R is equals to K dt. Now, integrating this equation, we get natural logarithm of the molar concentration of R is equals to minus Kt plus I, and this is now our equation 4. Again, I is the constant of integration and its value can be determined easily. When t, that is time, is equals to 0, R is equals to R naught, where R naught is the initial concentration of the reactant. Therefore, equation 4 can be written as natural logarithm of molar concentration of R naught is equals to minus K into 0 plus I, and therefore, we will get the value of the integration constant, that is ln molar concentration of the R initial equals to I. Now, substituting the value of I in equation 4, we get ln R is equals to minus Kt plus ln molar concentration of R, that 0, that is naught. Now, on rearranging the equation, we will get ln molar concentration of R upon R naught is equals to minus Kt, or K is equals to 1 by T natural logarithm, that is ln R naught by R. Now, this is our equation 6. Now, at time t1, from equation 4, natural logarithm of R1 is equals to minus Kt1 plus ln R naught. Now, this is 7th equation. Now, at time 2, ln R2 is equals to minus Kt2 plus ln R naught. Again, this is equation 8. Now, where R1 and R2 are the concentration of the reactants at time t1 and t2 respectively. Subtracting equation 8 from equation 7 comes out to be ln R1 minus ln R2 equals to minus KT1 minus KT2. Now, on rearranging, the expression becomes ln R1 by R2 is equals to minus K T1 minus T2. It will come out to be K T2 minus T1. Now, the expression for K will be 1 upon T2 minus T1 ln R1 upon R2. Now, this is the equation 9. Now, equation 5 can also be written as ln molar concentration of R upon R naught is equals to minus Kt. Taking antilog of both the sides, we get molar concentration of R is equals to R naught E raised to power minus Kt. Now, comparing equation 5 with y is equals to mx plus c, if we plot ln R against t, we get a straight line with slope is equals to minus k and intercept equals to ln R naught. The first order rate equation 6 can also be written in the form k is equals to 2.303 upon t log R naught by R. Log R naught by R is equals to Kt divided by 2.303. Now, if we plot a graph between log R naught by R versus t, the slope is equals to k by 2.303. This plot shows you log R naught by R versus time for the first order reaction. Hydrogenation of ethene is an example of first order reaction. Ethene C2H4 plus H2, the hydrogen, gives C2H6, that is ethane. Now, it is the first order reaction, so the expression for the rate will be equals to K molar concentration of C2H4. All natural and artificial radioactive decay of the unstable nuclei takes place by first order kinetics. There is an example of a first order kinetics. A radioactive reaction is given in front of you. Radium is changing into helium and radon. Rate is equals to K molar concentration of radium. Another example, decomposition of N2O5 and N2O are some more examples for the first order reactions. Let us consider a typical first order gas phase reaction. A gives B plus C, all are in the gaseous state. Let Pi be the initial pressure of A and Pt the total pressure at time t. Now, the integrated rate equation for such a reaction can be derived as total pressure Pt will be equals to Pa plus Pb plus Pc, and the pressure unit will apply, where Pa, Pb and Pc are the partial pressures of A, B and C respectively. If x atmospheres be the decrease in the pressure of A at time t and 1 mole each of B and C is being formed, the increase in the pressure of B and C will also be x atmospheres each. Now, the equation is again A gives B plus C, all in the gaseous state. Now, at time t is equals to 0, P initial in atmospheres for A, then the pressure for B and C will be 0 atmospheres. Now, at time t, partial pressure Pi minus x atmospheres for A and for B and C will be x atmospheres each, where Pi is the initial pressure at time t equals to 0. Now, calculating the total pressure, it will be equals to Pi minus x plus x is equals to Pi plus x. Now, the value of x will be equals to Pt minus Pi, where Pa is equals to Pi minus x is equals to Pi minus P total minus P initial. Therefore, it will come out to be 2 Pi minus Pt. K is equals to 2.303 upon T log Pi upon Pa. It is equals to 2.303 upon T log Pi divided by 2Pi minus Pt. Now a numerical problem in front of you. The initial concentration of N2O5 in the following first order reaction. N2O5 in the gaseous state gives 2NO2 in the gaseous state plus half O2 again in the gaseous state was 1.24 into 10 raised to power minus 2 moles per liter at 318 Kelvin. The concentration of N2O5 after 60 minutes was 0.20 into 10 raised to power minus 2 moles per liter. Calculate the rate constant of the reaction at 318 Kelvin. Now let's solve this problem. For the first order reaction, we have the expression log R1 by R2 equals to A T2 minus T1 by 2.303. Now putting up the value and first of all rearranging the equation, K will be equals to 2.303 divided by T2 minus T1 log R1 by R2. Now I am just putting the value 2.303 divided by 60 minutes minus 0 minutes log 1.24 into 10 raised to power minus 2 moles per liter divided by 0.20 into 10 raised to power minus 2 moles per liter. After calculation, it will come out to be 2.303 divided by 60 log 6.2 per minutes. The value of K will be equals to 0.0304 per minute. Now let me take another example. For a first order reaction, calculate the time required to reduce the concentration of a reactant from 10 grams to 3 grams. Given the first order reaction rate constant is 2.51 into 10 raised to power minus 3 per second. Now let's solve it. The initial concentration of the reactant R0 is equals to 10 gram. The final concentration of the reactant is RT is equals to 3 grams. The rate constant given is 2.51 into 10 raised to power minus 3 per second. Now for a first order reaction, we have K is equals to 2.303 upon T log R0 by R. Now rearranging the expression, it will come out to be T is equals to 2.303 by K log R0 by R. Now putting the values, 2.303 divided by 2.51 into 10 raised to power minus 3 log 10 by 3. The time will come out to be 0.48 into 10 raised to power 3 seconds. Now the half-life of a reaction. The half-life of a reaction is the time in which the concentration of a reactant is reduced to 1/2 of its initial concentration. In other words, half-life is the time required for the completion of half of the reaction. It is represented as T half. Half is in subscript. Now let's calculate and find out the half-life for the zero order reaction. For a zero order reaction, the rate constant is given as K is equals to R0 minus R by T. At T, that is equals to T half, R is equals to R0 by 2. Hence, the rate constant at T half becomes K is equals to R0 minus half of R0 divided by T half. Now, T half will come out to be R0 divided by 2K. It is clear that T half for a zero order reaction is directly proportional to the initial concentration of the reactants and inversely proportional to the rate constant. Now let's find out half-life for a first order reaction. For the first order reaction, we know that K is equals to 2.303 by T log R0 by R. So at time T is equals to T half, R will be equals to R0 by 2. Hence, K is equals to 2.303 by T half log R0 by r naught by 2. Therefore, t half will be 2.303 k log 2. Now, putting the value of the log 2 in the expression, it will be 2.303 upon k into 0.301. Hence, t half for first order will become 0.693 by k. Now, from this equation you can see that for a first order reaction, half-life period is constant. That is, it is independent of initial concentration of the reacting species. The half-life of a first order reaction is readily calculated from the rate constant and vice versa. For a zero order reaction, T half is directly proportional to initial concentration. For a first order reaction, T half is independent of the initial concentration. Now let me take some questions based on half-life. The first example is, a first order reaction is found to have a rate constant K is equals to 5.5 into 10 raised to power minus 14 per second. Find the half-life of the reaction. Now let's solve it. The half-life for a first order reaction is T half is equals to 0.693 by K. Now just putting the value of the K, T half is equals to 0.693 divided by 5.5 into 10 raised to power minus 14 per second. So after calculation, T half will be equals to 1.26 into 10 raised to power 13 seconds. Now another example. Show that in a first order reaction, time required for the completion of 99.9% is 10 times of half-life of the reaction. When the reaction is completed 99.9%, then R is equals to R naught minus 0.999 R naught. K is equals to 2.303 by T log R naught upon R. Now K is equals to 2.303 by T log R naught divided by R naught minus 0.999 R naught. Solving it, K is equals to 2.303 divided by T log 10 raised to power 3. The expression will come out to be T is equals to 6.909 by K. For half-life of the reaction, we know that T half is equals to 0.693 by K. Now just comparing the two expressions, T by T half is equals to 6.909 upon K into K upon 0.693. It comes out to be 10. Now let me take another example based on half-life period again. The half-life period of a first order reaction is 200 seconds. Calculate the rate constant for this reaction. For a first order reaction, the half-life is given as T half is equals to 0.693 upon K. Therefore, K is equals to 0.693 by T half. Now we have T half is equals to 200 seconds. Putting the values, K is equals to 0.693 upon 200. After calculation, it will come out to be 3.465 into 10 raised to power minus 3 per second. Again another example. The half-life period for a first order reaction is 45 minutes. Calculate the percentage of the reactant left after 180 minutes. Solving it, for a first order reaction it is given that T half is equals to 45 minutes. The rate constant for the reaction will be K is equals to 0.693 divided by T half. It is equals to 0.693 divided by 45 minutes. It is equals to 1.54 into 10 raised to power minus 2 per minute. The rate expression for the first order is given by K is equals to 2.303 by T log R naught by R, or we can write it as R naught by R is equals to exponential raised to power Kt, or R naught is equals to exponential minus Kt. At t is equals to 180 minutes, R by R naught is equals to exponent minus 1.54 into 10 raised to power minus 2 into 180. Calculation, and it will come out to be 0.0625. Therefore, after 180 minutes, only 6.25% of the reactant is left. Another example based on zero order reaction. The question is, for a zero order reaction, the rate constant is 0.14 moles per liter per second. If after 2 minutes, the concentration of the reactant is 0.15 moles per liter, calculate its initial concentration. Now, answer is, for a zero order reaction, we have K is equals to R naught minus R by T. The given value for K is equals to 0.14 moles per liter per second. Now, the molar concentration of R is equals to 0.15 moles per liter. Time t is equals to 2 minutes. Converting it into second, it will be 2 into 60 seconds equals to 120 seconds. Now, putting the values in the expression, R naught is equals to K into T plus molar concentration of R. Values putting 0.14 into 120 plus 0.15 moles per liter. It will be now 16.8 plus 0.15 moles per liter. After calculation, it will be 16.95 moles per liter. Now, table 1 summarizes the mathematical features of the integrated laws of zero and the first order reactions. The table 1 shows you the integrated rate laws for the reactions of zero order and first order reactions. Now, let me take up the new concept, that is zero first order reactions. The order of a reaction is sometimes altered by conditions. Consider a chemical reaction between the two substances. When one reactant is present in large excess, during the hydrolysis of 0.01 mole of ethyl acetate with 10 moles of water, the amount of the various constituents at the beginning T is equals to 0, and at the completion of the reaction, that is at time t, are given as under. That is CH3 COOC2H5 plus water gives acetic acid CH3COOH plus ethyl alcohol, that is C2H5OH. Now, for this equation and the reaction, the data is in front of you, and from the given data you can see that the concentration of the water does not get altered much during the course of the reaction. So, in the rate equation, rate is equals to K molar concentration of CH3COOC2H5 and the molar concentration of water. The term the molar concentration of water can be taken as constant. The equation now becomes rate is equals to K dash molar concentration of CH3COOC2H5, where K dash is equals to K into molar concentration of water, and the reactions behave as a first order reaction. Such reactions are called pseudo first order reactions. Another example of pseudo first order reaction is inversion of cane sugar. C12H22O11 plus water, it gives C6H12O6 plus C6H12O6. Now, cane sugar gives glucose and fructose. The rate is equals to K and the molar concentration of C12H22O11. Here again the molar concentration of the water is constant, so it can be ignored. Now, I am taking one more example based on this. Hydrolysis of methyl acetate in aqueous solution has been studied by titrating the liberated acetic acid against sodium hydroxide. The concentration of the ester at different time is given below. The data is in front of you and it shows that it follows a pseudo first order reaction, as the concentration of water remains nearly constant, that is 55 moles per liter during the course of the reaction. Now, what is the value of K in this equation? The rate is equals to K CH3COOCH3 and molar concentration of water. For pseudo first order reaction, the reaction should be first order with respect to ester when the molar concentration of water is constant. The rate constant K dash for pseudo first order reaction is K dash is equals to 2.303 by T log C naught by C, where K dash is equals to K into molar concentration of the water. From the data above, we can just put the values and it can be seen that K dash is equals to K molar concentration of water is constant and is equals to 2.004 into 10 raised to power minus 3 per minute, and hence it is a pseudo first order reaction. We can now determine K from K into molar concentration of water equals to 2.004 into 10 raised to power minus 3 per minute. Now, putting the value K into 55 moles per liter equals to 2.004 into 10 raised to power minus 3 per minutes. After calculating, the value of K will be 3.64 into 10 raised to power minus 5 per mole liters per minute. Now, let me summarize what we have studied today. In this module, we have learnt about the integrated forms of the rate law equations for the zero and the first order reaction. A reaction with the zero order means that the rate of the reaction is proportional to the zero power of the concentration of the reactants. In the first order reactions like R giving the products P, the rate of the reaction is proportional to the first power of the concentration of the reactant R. The integrated rate equations for the zero and the first order reactions were derived. The half-life of a reaction is the time in which the concentration of a reactant is reduced to 1/2 of its initial concentration. For zero and the first order reactions, the half-life periods were derived. There are also some reactions called pseudo first order reactions. These reactions are higher order, but actually they follow the first order kinetics. So, dear students, I hope you have understood the integrated rate equations, the concept of the half-life and the pseudo order reactions. Their derivations and the numerical based on these issues are very important for the examination point of view. Thank you so much.